Okay, all right. Well, happy Friday. Happy week one Friday. We are spring quarter. Okay. So what are we looking at today? I wrote expanding linear regression and matrix notation. So on Wednesday we used matrix notation, and we worked out the solution for ordinary least squares regression. We said, we've got this matrix of weights, okay? And for linear regression, those weights are just the intercept and the slope. And we said those are W. And what we do is we say, what is our loss function, right? Our loss function is basically our target values minus our predicted values, T minus XW. And we square those values and we sum them up, right? And so it ends up being T minus XW transpose times T minus XW. We add those up, we divide by N to get the mean squared error. And then what we said was, okay, let's take the gradient, basically the derivative of this thing. We'll set it equal to 0, and we solve for W, that where the gradient is going to equal 0, and that's basically going to correspond to our local minimum. And so so we did this on Wednesday. So this is our loss function after we kind of expanded out. And then we take the gradient of the loss function with respect to W. And this is what we get. We use kind of our useful little gradient relations, okay? And then we solved for W. So solving for W leaves us with kind of the weights that will minimize our sum of squared errors. Is going to be X transpose X inverse X transpose T, which I think looks familiar for a lot of us. Often we see X transpose Y, but in our case, T is our target values instead of Y. And that's where we kind of left off. And so let me give you that, right? So that's our kind of ordinary least squares regression result. Here is just a very, very, very simple example. I have the X values 1, 2, 3, 4, and our Y values are 1, 3, 2, 4. So so they're not in a perfect straight line. Okay, and I say, okay, well, what is the regression line that's going to minimize the sum of squared errors here? Well, we can say to make our X matrix, we will bind a column of 1s to our X values, and so this is going to be a n by 2 matrix, okay? And I have 4 observations, so 4 by 2. And then what I would do is I would do X transpose X, and so even though I've got n rows, when you do X transpose X, you end up with a 2 by 2 matrix, okay? And we do X transpose X inverse, which is also a 2 by 2 matrix, but now it's different numbers, right? So this was, I forgot, our projector cuts off a little bit here. Okay, so I've got X transpose X, this 2 by 2 matrix, and we take the inverse of that. And this feels weird, but if I do the inverse of X transpose X, X transpose X inverse, the inverse operation in R is solve. I don't know, it's a little bit of a weird thing, but you do so X transpose X inverse is solve Tx times X, and then we'll multiply that by X transpose X inverse times the transpose of X, which will give me a 2 by 4 or 2 by n matrix. And then if I multiply that by my target values, which has n values in one column, that will reduce it to a 2 by 1, which is equivalent to our W hat. And so these are the two weights in our W matrix, which would be 0.5 for the intercept and 0.8 for the slope. So just kind of working through all of this, X transpose X inverse X transpose T gives me a 2 by 1 thing. And we can see, even if here I had 4 observations for n, but I could have 1,000 observations for n, and it would still, because of the matrix operations, boil down to a 2 by 1. Okay, and we can confirm, are these indeed the intercept and slope that would minimize the values are equal to the OLS solution. And so if I run the R's LM function, and not that this is a proof or anything, but I think we come to a point where we trust LM on R. Okay, so if I do LM and I do T as predicted by X, it gives me the intercept of 0.5 and 0.8. What happens underneath the hood in for LM is not this matrix stuff that we've been doing. And actually, I don't actually know what happens. I think it calls a C function, and basically when it calls a C function, it's like, oh, magic. But we have an intercept and we have a slope, and indeed the LM function in R produces the same thing that we get when we do our matrix operations. Okay. If we wanted to see what our model predicts, we could take our X matrix and multiply it by W hat. Okay, and so these would be our predicted values, our T hats, so X times W hat, so X again being n by 2, W hat being 2 by 1, so n by 2 times a 2 by 1 is going to give you n by 1. We get n values, we get a predicted value for each of our n observations, and these are predicted things. And I can plot the T hat values, and that is what these red dots are. And so we could see, the first observation we predict 1.3, the next observation is 2.1, this observation is 2.9, and this one's 3.7. So we can see these are our predicted values, and we have residuals and whatnot. Okay. Okay, so let's try let's take a look at this data set again. So I introduced this same data set, right? The Olympic things, and we said, hey, you know what? We're looking at the race times for the 100-meter dash. Seems like it's getting faster and faster. I don't know what the floor is for the 100-meter dash, right? Because it felt like, just in your brain, you feel like, okay, there's got to be a point where they can't get any faster, but it looks like they're still getting faster. So I don't, so who's the fastest person on the planet, right? Usain Bolt is like the record holder, and still, I don't know. He's not getting younger though. All right, so if we said, let's just fit a linear model, right? Linear model, not probably the greatest idea, but let's just try it out, okay? Linear model seems to indicate this is our intercept, this is our slope. Every year, we're getting faster by 0.013 seconds, so like 1/100th of a second. Basically every 3 or 4 years, we drop maybe 5/100ths of a second. Am I saying that right? Okay, so this is what the linear model says. Okay, and so our X this time is the year 1896, 1900, 1904. Okay, and I'm going to bind a column of ones, and what do? I do what is our predicted values? X transpose X inverse, X transpose times our actual target values, the T's here, and it gives me W hat. I get 36.309 for the intercept, a slope of negative 0.01327, which is exactly what LM does, right? LM 36.309, negative 0.01328, which is what we have here, but just rounded a little bit. So it's the exact same value. So no surprise. All we're saying so far is that, yeah, X transpose X inverse, that business works. And again, if I plug in our W hat and I multiply it by our X matrix, these are my predicted values, okay? And I can plot those, and this is the straight line. And we go, okay, that looks reasonable. That looks reasonable. Okay, what if we want to have something that's not a straight line, right? What if I want to include like a quadratic term or something like that? We can do that, all right? And it will still be a linear regression model. Okay, before I keep going on, let me give you your view quiz answer. First one today is the letter A. A as in apple. A as in apple is your first view quiz answer. All right, so here I'm going to just say, let's take our X matrix and let's add a third column. And this third column will be my X value, and I'm going to raise it to the second power. Okay, so basically I got our X value raised to the 0, raised to the first, raised to the second power, right? And so I raise it to the second power. And so these values are not linearly related to x1 and x2 and so on and so forth. There's a quadratic relationship. But when we combine them into our values to make our predicted values, we combine them in a linear way, right? We could just imagine this third column being something, and it's going to be some coefficient times 1, or some kind of weight times x1, and some kind of weight times this value, whatever it is, and we're just kind of combining them in a linear fashion. So it's still a linear model, it's just that this third column is not linearly related. It is related to this column, but not in a linear fashion. So see, we still have a linear model, we just don't have linear terms there. And so if so I can do this in R. I can do, here's our column of 1s. Here is the column of X values, 1896, 1900, 1904. And then what do we get when I square them? I get these really big numbers, right? 1896 squared is like 3.6 million, and so on and so forth, okay? And that's what we do. And then I can say, all right, let's solve for the W that's going to figure this out, right? And so my model, my predicted values are going to be our W0. We have an intercept, we have a weight for the X term, and we have a weight, a W2, for the X squared term, okay? So we have a W0, a W1, and a W2. We'll gather those three weights into our kind of weight matrix, W. And if we do that, then our predicted values are still W transpose X, okay? W transpose X sub n for our predicted value for X sub n, okay? And if you just kind of ignore the dimension of W and the dimension of X, this is exactly what we had when we only had, when we didn't have this quadratic term, right? It's the exact same kind of predicted thing. And so what are my predictions for all of the all of the values in X? Okay, it's still going to be X times W. Okay, and this still matches exactly what we want, right? X times W gives me all of this. This is exactly what we want. It's the same in terms of matrix notation. It's exactly the same, even though I'm adding a third column. And therefore, the loss function is exactly the same. T minus XW transpose times T minus XW. Okay, and this is kind of the beauty of working in linear algebra. Okay, for these kind of linear models, is that we can add terms, right? So on Wednesday we said one way to kind of solve for the weights is to do partial derivatives, and we can do the partial derivative with respect to W0 and the partial derivative with respect to W1, and we can solve for that. And if you were given this assignment, now that you have a quadratic term, you'd have to find the partial derivative with respect to W0, partial with respect to W1, and the partial with respect to W2. And it becomes a lot more work, But here, we work in linear algebra, we work in matrix notation, and we say, oh, this is the exact same problem that I had before. The dimensions in my X are different. The dimensions in my W are a little bit different, okay? My T is still n by 1. And everything is exactly the same, and therefore if I go through the exact same process of let's take the gradient of the loss function with respect to W, set it equal to 0, and solve, we're going to get the exact same answer of X transpose X inverse X transpose T. Okay, so it really doesn't matter how many columns you have in X. If you're solving for the value that's going to minimize this, you're going to end up with this. Okay, and so that's kind of cool. This is kind of one of the big reasons why we work. We choose to work in kind of this matrix notation, because even though there's kind of this hurdle in the beginning, it ends up making our life easier in the bigger picture. Okay? Is that okay? I kind of just waved my hands and said, remember what we did? And it still works, okay? So this is our solution. And so we go, okay, all right, well, let's work through this and let's apply it to our thing. So I say, all right, here, let's look at my matrix. What do we get? Okay, so this is my Olympic data, right? So I have my X matrix, right? Column of ones, my column of X's, my column of X squared values. And I say, all right, let's take this and do X transpose X inverse X transpose T, because that's our answer. But what happens when I try to do that, right? So here my X, this is my column of ones, and the second column is 1896, 1900, 1904, and the third column is, X squared, something like 3.6 million, whatever. When I ask R to do this, I get an error, okay? It says error in solve X transpose X, this thing, right? X transpose X times this, I get an error in this solve thing. System is computationally singular, reciprocal condition number equals this. All right. What do you think is going on? Why do you think I'm suddenly getting an error? I just said, hey, it's the same solution. We could just do what we did before and get our answer, but apparently I can't. Any guesses as to why this is happening? Yeah.
Is it too close to like a non-invertible matrix?
Well, in the computer's eyes, it is. It's not. It is an invertible matrix, okay? There's nothing inherently wrong about this matrix, but the computer has trouble. And the reason why is when I do X transpose X, okay? X transpose X, remember that X squared column is, they're big numbers, like 3.6 million, right? And then so if I do X transpose X and I do 3.6 million times 3.6 million, I don't know what I get. I get these really big numbers, okay? And then I'm summing them up, right? So I should be getting a 3 by 3 matrix, and I do, but look how big this last number is. It's 4.09 times 10 to the 14, okay? Now, floating point numbers, they can handle big numbers, right? 4.4 times 10 to the 14, but what happens when I try to inverse this or calculate the inverse, right? Now we're kind of getting like 1 over, a really big number, okay? And we know floating point numbers, there's a limit, right? It approximately can get around to 10 to the negative 16 before like you start running up, your machine epsilon is around 10 to the negative 16. And so we start running up into problems of trying to do 1 divided by this really big number and trying to add it to things, and it basically blows up the computer. I mean, not literally, but just like we can't. It's like this sci-fi movies on Star Trek, right? Like okay, nobody knows what I'm talking about, but like the keyboards start exploding under your fingers. But basically, yeah, if you take the year 2000 and you square it, you get 4 million, and then when you try to do the inverse operation on this really number, we basically run into a computational instability. Okay, and so R just says, hey, we can't find the matrix inverse, and that's not true. The matrix inverse does work if we were able to work with real numbers. It's just that on the computer, we're not working with real numbers and things break. And so it's kind of like one of those things where when you're dealing with computational things on the computer, you have to keep in mind we run into some of these things. And you end up having these weird things where it's like, okay, I can't deal with the year. I've got to like make an adjustment. So we can say like, okay, let's subtract 1800 from every single value, or let's subtract, or let's divide everything by 100 or something. So here, one kind of way I'm going to circumvent this is I'm going to say, all right, instead of dealing with 3.6 million, okay, I'm going to just multiply it by 1 over 10,000, 0.0001. Okay, so this is basically the same matrix, it's just I've moved the decimal point over here. Okay, and now R is like, oh, these are nice little numbers. I can work with this, and it is able to solve for x transpose x inverse x transpose t and whatnot. Okay, this coefficient now is a weird thing because it's not the year scaled, but it's like I don't know, 18.96 squared and 19.00 and 19.04 squared, which is a little bit weird, but in this case it works. Okay, so with our scaled values, we can now calculate the matrix inverse, and we can do this here. Okay, so the inverse works or exists. It's just we had to do stuff to avoid computational instabilities here. Okay, let me give you your second view quiz answer, which is the letter E. E as in elephant. E. Okay, so now we have an intercept, we have a slope, and we have a coefficient that goes to our x squared values, but again, our x squared values are like weird, not exactly our x squared. Okay, if I were to solve the same thing using LM, I could do it. Okay, you can take a matrix and you can say calculate a linear model using a matrix here. When you do that, in this case, my matrix has a column of ones, and so the column of ones, the coefficient that corresponds to the column of ones is equivalent to an intercept, and so R does not need to calculate its own intercept. By default, it tries to calculate an intercept, but in our case, I have a column of ones, so I don't need an intercept. I would actually run into a problem if I say calculate an intercept and I have a column of ones, because those are linearly the same, or they are the same. So what you do is you do a 0 plus. 0 plus in the LM notation means don't calculate an intercept term, and so we get three coefficients: coefficient for each of the columns, coefficient for column 1, coefficient for the x column, coefficient for the x squared column. Okay, and these are our coefficients, and they are exactly the same as these coefficients. Okay, so we have that. So that's what this is 0 plus is when we use LM. Okay, and then if we wanted to, we can calculate the fitted values. The fitted values are same thing. X. This time we're using, again, we modified our X matrix, so we have to use our modified X matrix. That is, so I have this X underscore SC to indicate my scaled, where I scaled the values in the third column, and I plug that in, and I do, our scaled X values times W hat, and these are our values, 11.32, 11.22, and so on and so forth, and we see these things improve. And I can plot this, and this is the fitted line, okay? And again, it looks like it does a decent job fitting. So this is slide 34, and if I compare it to this, like, if I looked at this, I'd go, oh, that looks pretty good. And then I look at this, I go, oh, that looks pretty good too, right? It's kind of hard to judge fits, in my opinion. Like we have a sense of like when something's bad, but we go, oh, these look pretty good. The linear fit, you don't want to where did it go? You don't want to extrapolate forever because you'll eventually get like negative values, okay? And then over here, you don't want to extrapolate forever because eventually the world record times will start climbing up, right? And so that's also no good. Or not the world record times, but the winning times will start climbing back up. And so, all the same kind of rules about extrapolation and only kind of using your model to make predictions for where you've collected data, all of those things still apply. But that's what we have. Okay. All right, so that's, now we can do quadratic fits here. And we go, oh, well, that looks good. What if instead of a quadratic fit, I wanted to do like a cubic fit and things like that, okay? There is, and we could do, take our x column and we can cube it, and then if we wanted to have a fourth order term, we can take our x column and raise it to the fourth power, and so on and so forth. There's actually a function in R called poly, and this will kind of create columns that have, polynomial terms. So we don't end up with these issues of having values that are too highly correlated. How can I illustrate this? So if you have a, do I try to point this at this? You can't even see it on here. So this would be kind of your linear term, and then your quadratic term would look something like this, and then your cubic term would, look something like this, and your fourth order term would look like this, and your fifth order term. And basically, you end up getting, if you just do x squared, x cubed, x to the fourth, and you're just kind of dealing with positive numbers, all of these things end up having like very, very high correlations. You have correlations of like 0.99, 0.98, and it's basically all of them as x gets bigger, x squared, x cubed, x to the fourth, x to the fifth, they also all get kind of bigger. And we know that when terms are highly correlated, your estimates become more and more unstable and more susceptible to little variances here. Okay, and so one way to kind of avoid that is we can use this function poly. Okay, poly kind of scales the values. So you end up having these uncorrelated polynomial values. So what it will do instead is it will just kind of, for your, for the range of x, if your range of x is linear, is this segment, is going to say, okay, from here to here, whatever these bounds are, right? So even if it's like 0 to 10 or something like that, it's going to say, all right, what we're going to do is we're going to calculate the squared terms to be kind of like this. All we're doing is we're just kind of, so the quadratic thing will look like this. And what's the correlation between the quadratic and the linear part? The correlation between these things is 0. Okay. And and then for the cubic, it'll find something like this. All right. And the correlation between the cubic thing and the linear is 0, and the correlation between the cubic and the quadratic is also 0. And so it finds these uncorrelated things, which allow us to kind of find, what is the contribution of just this one specific component, right? So poly will kind of scale the values and create uncorrelated polynomial values, at least for this particular range of x. And again, once you go outside of the kind of range of x that you've defined, they start, becoming correlated once again. Okay. As far as the poly function does not create a column of ones. So if I do poly x2, column 1 is linear and column 2 is quadratic. Okay. And this is what it looks like, okay? And it says, okay, these are your intercept. This is your intercept, your slope, or weight for column 1, and your weight for column 2. These no longer have, meaning for us, okay? Because we had to kind of process it through this poly function, okay? So, we have to process it through the poly function to kind of get our coefficients. And so now things are just kind of weird, all right? But if we do LM, fit this LM model, and we look at this and we can say, hey, what are my fitted values? We do get fitted values. And if I plot them, they would end up looking exactly like this, okay? So if I look at these fitted values, 11.322, 11.228, 11.1366, these are the same values, 11.322, 11.228, 11.1366. So using the kind of the polynomial, the poly function here, when I said, hey, make a, take our X matrix and kind of make a polynomial matrix with the second order term, the fitted values are exactly the same as the fitted values when I did this operation, right? The fourth value, 11.091923, and this is what exactly 11.091923. So it's the exact same values, even though because we've used that poly function, we've lost a lot of interpretability, right? So this is one of the trade-offs. You use poly, you get some nice things, nice properties of it, but you lose some interpretability. Okay. Yes, I wrote, an unfortunate side effect of using poly is that all of the X values get transformed, so interpretability of coefficients is dramatically reduced. The coefficients only make sense for the transformed values, okay? But it is still very useful, and what we can do is we can use this poly function to try fitting a whole bunch of different ordered fits, okay? So here, I'm gonna just try fitting a whole bunch of models, right? So I said, okay, let's fit a linear model where I have a quadratic term. And now, rather than having to expand my X matrix manually and whatnot, I'm just gonna use this poly function. I'm gonna say, let's include a third order term, let's include a fourth order term, let's include a fifth order term, a sixth order term. And we just wanna see how does our fit improve as I keep increasing the order of my polynomials, okay? So I have my poly, third order model, fourth order model, so on and so forth. And I'm gonna go ahead and I'm gonna just plot all of the fitted values for each of these things. So I've got my linear fit, second order fit, third order fit, and we're gonna plot them in red, orange, green, blue, purple, and I guess dark gray. And what does this look like? It looks like this, which is kind of pretty. And I ask, okay, which line is the best fitting line? And we go, well, they all look kind of good. But, and one thing you notice is that there's this one kind of outlier. In 1896, the fastest time was 12 seconds, and then in 1900, the fastest time was 11.0 seconds. And I think that was because they didn't have stopwatches that went any more precise than a whole second, right? So it was like, okay, I'm counting 1, 1,000, 2, 1,000, 12 seconds. You're the winner. I don't know how they recorded time, right? But 1896, it was 12.0 seconds versus 11.0 seconds, and then in 1908 they're like 11.2 seconds. I don't know how they measured time and stuff, and so we're just trying to, a lot of these end up just trying to fit this one unusual point. Maybe we should throw that away, and in between we just kind of have this rainbow spaghetti here, and what is kind of the best fit. We can start seeing there's a little bit of trouble because look at this purple line. It's like starting to take a dive. It's like, ooh, we're going to get rapidly fast really, really quickly, and we go, oh yeah, that probably doesn't make sense. So what do we do? Okay, but anyway, this is kind of where we are. We if we were to measure our R-squared values, okay, and we say, hey, which one of these minimize the sum of squared residuals, what are we going to find? We're going to find that the higher order fits do a better job, right? Your R-squared values, you can always kind of tweak out and eke out a little bit more R-squared values if you just kind of keep adding more terms. And so in your 101A, what did you learn? Like how do you avoid just saying we're gonna fit 80 terms and get an R squared of 0.995. You learn things like, okay, we'll add a penalty, right? And we say, how many terms do you have? We're going to have a penalty of the AIC and the BIC, kind of add little penalty terms there. Or you can do, I can't remember, my brain is breaking on me. Likelihood ratio, is that right? What is it? Where you like compare one model to another model and you do like the F ratio, the F test? Yeah. Like my brain suddenly stopped working for a second. You do a likelihood ratio test, right? Where you basically say, okay, I'm losing this many degrees of freedom by adding these additional terms, and so is the improvement that I'm getting like worth the loss in the degrees of freedom and things like that. Okay, so those are fine ways to do it. Okay, and so this is we've probably seen this thing, right? We call summary on the thing, and we go, okay, if I do summary on the third, the model with the three things, I think when I kind of start off, it's just like, oh, I keep looking for stars, and if I look for the stars, then it's like, okay, these terms are significant, so let's include them, right? And then, and if I try to fit like this sixth order model, right, I go, okay, let's look at these stars. What is the p-value for each of my coefficients? And I go, okay, I've got a star for the first column, second column, third column, but then no more stars for the fourth, fifth, and sixth. I go, okay, this model, we don't need these ones because I don't, the p-values associated with these things are low and things like that. And that was kind of like, I don't know how you did model selection, right? It was often kind of this kind of just, let's, do I want to include this term? And if I want to include this term, do I have like a star going there or not? And if I don't have a star, we throw it away. Which is, I guess, okay. But it's probably not necessarily the best method. And even with this model, okay, we say, all right, we have, the first order term, so the linear term, the quadratic term, and the cubic term, they all end up being significant. And we go, okay, well, that looks good. And then someone says, okay, well, help me understand what that means. And how would you interpret this, right? So you say, okay, when I look at the sixth order model and the third order model, it's the linear component, the quadratic component, the cubic component are significant. The fourth order, fifth order, and sixth order parts are not significant. So we're going to say, okay, let's use this cubic model. And someone goes, oh, okay, great. Now, what does that mean? And how would you explain this? The linear model, that's kind of easy. As x gets bigger, as the time has gone on, people have gotten faster, and there's kind of this linear thing, right? And now we say, okay, there's this cubic aspect to it. As time goes on, x changes in a cubic fashion. I have no idea what that means to say like the race time has kind of this third order relationship with the year in which the Olympics were held. We lose a lot of interpretability, and even kind of this quadratic thing. How do you explain that? Because the quadratic kind of implies this parabolic shape, and so that doesn't quite make sense. And so once you start going above this linear term, right? Like in physics, there are some like nice little quadratic things, right? It's just like, oh, inverse squared things, right? Like the farther you get away from, the sun, the effect of gravity you feel is different and stuff like that. And you have these nice little things that kind of make sense. But then now we have this, and it was just like, oh yeah, our fit seemed to go up when we include a quadratic term. Our fit seemed to get a little bit better when we included a cubic term. And it didn't improve when I included a fourth order term. I think we start losing a lot of interpretability. And so what we end up kind of doing in machine learning is we say, I'm not going to worry about interpretability. I'm going to just see if I can get better predictions, okay? And the way we're going to measure our prediction performance is via cross-validation, okay? So we're kind of shifting away from kind of this classical approach. So, your 101A, and I love 101A, so don't get me wrong with when we start moving away from linear regression, right? So linear regression, great interpretability, some of the coolest models you can make, right? Some of them and highly interpretable, but there is kind of a limit in terms of their usefulness and even the interpretability once you start including these other like higher order polynomial terms, because I don't even think anybody can really explain like in real life what is a sixth order polynomial, and like is there anything in real life phenomenon that has like a sixth order polynomial relationship with anything? I don't know. Okay. And so so we move away from that. We start and we just start focusing on, okay, how good is my model? The way I'm going to measure my model is if I put in a value and I get a prediction, is my prediction any good? Okay. And if it comes out good, then it's got to be good, right? And that's how we're going to start measuring things. And so we'll look at how we measure things via cross-validation, and that's going to be kind of our primary tool for evaluating how successful we are. How many of you? I given you two? Okay. The third view quiz answer today is the letter B. B as in bear is our third view quiz answer. B as in bear. Okay, I guess we're finishing a little bit early, but yeah, that's where we're going to go. Everything's going to kind of come down to just testing and see like how good of a prediction can I make, and so that's what we'll see next week. All right. All right, have a great weekend. Happy Easter to those of you who observe, and we'll see you all on Monday.